So good afternoon, everybody. My name is Jeremy Boxberger, and I'm working for Intrinsic. Today, the webinar will deal with structural optimization using Tosca and Abaqus. So let's start by introducing Intrinsic. Intrinsic is a company established in 1998 as a consultancy as an engineering consultancy company using old Dassault system products. It is a PLM consultancy that operates alongside engineering business. It is the UK largest and best resourced Dassault system business partner. It employs 64 people, and about the PLM business and the engineering consultancy employed 85 people. We have 4 offices in UK and 1 in South Africa. So we are, Intrinsic can provide PLM solutions for different panels, such as Studio Experience, CATIA, Enovia, Delmia, Simulia, and so on. And there is also, Intrinsic can provide consultancy to implement for the implementation or the product management, and also can provide software development and also support for like training, help desk. Intrinsic also can provide engineering services like design consultancy through concepts to detail design, material and process selection, prototype supplying and component testing. We are able to do some FE analysis as well on component or assemblies, linear and non-linear analysis, thermal, dynamic, and so on, vibrating. And to finish, there is the capability for expertise with press-to design, steeling, pattern design and research, casting and mold tool design, jig and fixture, vehicle installation, and so on. So today the webinar will deal with Tosca optimization. So we'll see what consists an optimization. Then we will see the different types of optimization, and we will see the different modules embedded inside Tosca. And we will see a more specific example on Tosca structural topology optimization. So today's engineers aspire to develop innovative products in the shorter development time, and they are to deal with security, comfort, performance, efficiency, durability, and so on. And these are just some aspects of the to take into account for a project. So why we are doing optimization? So in order to improve durability, to reduce the stress, to increase the frequencies, to maximize the stiffness, or to maximize the stiffness-weight ratio, and so on. So there's 2 main groups of optimization, 2 families, I would say. So the first family is the parametric method. It's the most common and used and well known in the CAD activities. And also there is non-parametric methods. So Tosca deals with non-parametric methods. So I will explain a little bit what are the different types. So in traditional development processes, the designer and engineer begin with a detailed solid model generated within the CAD 3D, and which is then subject to a number of design iterations based on the result of simulation, for example, FEA or CFD, and the prototype test. Although parameterize this model are employing design and experiment technique can improve the efficiency of this approach, it can also lead to innovation being constrained by the parametric definition of the design. So, and At the opposite, the non-parametric model will is enabled for the development of more innovative concepts before committing to detailed 3D geometry. Tosca provides a powerful range of topology and shape optimization with both structural and fluid flow application. To complete a non-parametric topological and shape optimization technique are applied before locking the design down to a 3D parametric model. This can lead to both greater innovation and reduced development time at a concept stage. So I will explain a little bit more what is embedded inside Tosca, the different type of optimization. So there is 5 big families inside Tosca. So there is Tosca structure sizing, Tosca structure shape, Tosca structure bid, Tosca structure topology, and Tosca fluid topology. So what is the fluid optimization? So the fluid optimization is about optimize the flow of a design and to reduce the loss of pressure inside a tube or a component. So this is fluid optimization, which can lead to innovative shapes such as the green one compared to the original design, which is a simple and with a constant diameter. So by reconstruction, we smooth the topology to improve the flow inside the part. About Tosca optimization, what is sizing optimization? So sizing optimization is for optimize the sheet thickness for best static and dynamic behavior. So by reducing the weight, but we can keep the same stiffness of the structure. It's feasible for large scale applications with up to 1 million of design variables. We can apply manufacturing constraint. Clustering shell element thickness is also applicable. So what is shape optimization? So shape optimization is more to reduce the peak stress which can occur during an analysis. So it will smooth some critical areas to reduce the peak stress. About bid optimization. So bid optimization, it's an automatic determination of the location and the orientation of bids to increase the moment of inertia of the part. So it is fast and stable using special optimal criterion based on the spreading of the bedding stress. The solution is independent from the mesh. There is a fast convergence. There is a good transfer and easy interpretation of the results due to a low scattering. And to finish, Tosca can deal with topology optimization. Topology optimization is mainly to maximize the stiffness and by reducing the weight. And also, Tosca can deal with manufacturing constraints such as freezing the subdomains to minimize the member size or to maximize the member size of a rib distance. It can deal with also the casting restrictions such as the draft angle we can have a part. It can deal with the thickness, the tightness also, and the stamping restriction, the symmetry and the coupling. And obviously we can have a combination of some restrictions. So Tosca is directly embedded inside Abaqus CAE, so it allows the same capabilities with Abaqus CAE, such as the user interface, and also it will save the file in the same CAE file. So this example will be about a topology optimization. So I have on the left a part which I would like to optimize to reduce the rate, and to the right I have another part which is the same part but where I design all the space available around the original shape. So in order to see, I will explain what I did. So here I have already loaded the part inside Abaqus. So I already create some partition inside the part. So I will explain why I did that a little bit after. So the first thing, obviously, I will just explain what I did as a boundary condition and all the things to do before to perform an optimization. So such as a normal analysis in Abaqus, I have to set up the property of the material and then apply it to the part. So here in there it will turn the part green, which means the material is set on a part. Then I have to add the part in the assembly, create a step is the next step. So I have already created a step here, so I don't need to create another one. And about the interaction, I will just create a coupling between one point and the surface where I want to apply a load. So I create first a reference point, and then I will just create a constraint, which is actually a coupling. So I select the point, surface the slave surface. And now we can see the yellow lines, which means it's done. So I will apply some boundary condition now. So I will apply a pressure to complete the first load. So according to the coordinate system, I have to apply the load along z-axis, as I can see on the part. So here I will just pin this surface to simulate their pin to another part. And that's the additional pressure. So this part is now completely set up. We can create a job. Oh, before doing that, I have to create the mesh, obviously. Select the size of the mesh and also the region I want to apply. So here I will just do a simple tête mesh. So now I'm ready to create a job. And I will submit it. So this analysis is not too long. It takes about 30 seconds. I can obviously, like a standard analysis, have a look to the results. So now let's start the optimization. So in the optimization, you can first create an optimization task. Is it where I select which type of optimization I want? So there is topology, shape, sizing, and bid optimization. So here it will be a topology optimization. In there, I can select to freeze the boundary region, so it means that the optimization will not be applied around this feature. I just select here to not, because I can set up manually. And also in the advanced tab, I can select condition-based optimization. So basically, condition-based is a little bit simplified optimization analysis, where there is only the strain and the volume which is applied on the model as a constraint. And for general optimization, there is a lot more possibilities. But for simple optimization, such this example, it will be easier to use the condition-based optimization. And also we can select the number of design cycles. So by default it's 15. And this will determine the number of iterations to perform on the analysis. So more you have a number of iterations, and more longer will be your analysis. So then I will create two design responses. The first one will be the strain response, and the second one will be the volume response. So for the strain, I select the whole model. And for the volume, I will just select the feature I want to perform the analysis. So I can select each body I want. So each I select those two bodies, and I'm not selecting the other bodies because I will apply frozen area on this. So now I have to create an objective function. So it will be to minimize or maximize the strain as an objective. So for our example, we will select to minimize the design response. and then I create the constraint for the volume. So I can select a fixed value that I want to reach, but also I can set a fraction of the initial value. So here I want 40% of the initial value. And I can apply a restriction like a frozen area or symmetry or a member size in topology. So I just select the frozen area. So there's these two bodies. So first, and I will select after those surface where I apply the load. Otherwise, you will be able to remove mesh on this point, and I'm not interested to remove material around the pressure or force area. So I select those faces, press OK. At this point, I can create an analysis. So I just double click on optimization process, where I will specify if I want it to save at each single design or at the end, or only at the end of the beginning. So I have selected every cycles in order to analyze how the optimization progress in the time. And then I can submit the analysis and monitor it. So in this video, I have a little bit accelerate the time in order to take shorter for the video. Because in terms of time, it has to iterate 15 times the number of one analysis, so it will be 15 times 30 seconds, so it's quite long. And also I can monitor with some graphs. So now the analysis is finished. So what I have to do before to see the result is to combine all of these steps. So then I select all for the optimization cycles and submit it. The combining now is finished, and now I can see what is the results. So by default, you will see the last iteration So this is the last results calculated by Tosca. And I can see the evolution of the analysis through the steps. And I can also animate it. So now let's see what we can do with these results. So to extract the STL, I have to go in the tree and click on extract. And then this window will prompt, and I have to select STL and click which design cycle we are interested. And also we can specify a smoothing. If you select none, it will be the result you get without any smoothing. And you have to click on extract, and it will create the part. And then if I want to work with this part, I can open it in CATIA. In CATIA, there is a workbench. We can reconstruct the STL by using Digitalized shape editor. I will do an article for the blog about this in more detail if you are interested. Here I select the STL part, click on apply to extract the STL part inside CATIA. And at this point you can't use this part because it's not a part body, it's a STL. I have to reconstruct it, so I have to go in another workbench called Quick Surface Reconstruction. And there is a cool a tool. We can create an automatic surface, and doing that can create the external surface of this part to begin to rework on it. So now this is a surface, and I can close this surface in part design. And then we can apply additional feature on this part. So this is almost the end of the presentation. So what we have seen is from an original model, we have applied an optimization on it to reduce the volume and the weight of the part. So from this analysis, by keeping the same stress and the same stiffness of the part, we have reduced the weight from 4.3 kilos to 2.9 kilos. And also we have saved time by not doing a lot of analysis and iteration in CAD in order to find the final design. So it could be from 6 to 10 iterations to find the last and final design. compared to topology, where we are just doing the topology optimization and add constraint and then reconstruct the part in the CAD tool. And the final analysis to check if our final design is suitable for our specifications. So this is the end of the presentation. Thank you a lot for your attention. And if you have any questions, I will be pleased to answer them.